Ok. Start. Muito bem, boa tarde a todos. Bem-vindos mais uma vez a mais uma das pré-conferências do 27º Encontro Nacional Sociedade Portuguesa de Química. Como sempre, vou só esperar que os participantes vão entrando na sala e, como nas outras sessões, vamos ter aqui a organizadora do Encontro Nacional que nos vai dar as últimas novidades sobre a organização deste encontro. Neste momento estamos a ver as pessoas do YouTube e, ok, já estamos a ter uma audiência relativamente simpática, portanto. So, thank you very much for coming. Welcome to everyone for this final pre-meeting of pre-conference of the 17th National Symposium of the Portuguese Chemical Society. So today, as usual, we have Susana Costa, which is going to give us the latest news on the meeting. And after that, we have Professor Mara Freire that will be giving today's talk. So without any delay, I'll pass the word to Susana. Susana, please tell us about the meeting.
Thank you, Joaquim. Good afternoon to everyone, and thank you all for joining us in this final pre-conference before the national meeting of the Portuguese Chemistry Society, which will take place in Braga. I would like to give a very warm welcome to Mara and to thank her for helping us to raise interest and to publicize the meeting. I thank also all the previous speakers. So the meeting will start in just 2 weeks from today, and I want to give you a very brief update. The final program will be disclosed today at the meeting website, along with other important information regarding attendance. As you will understand, we took a little bit longer to disclose the program because we have to manage the numbers of the pandemic. And managing these numbers and organizing a scientific meeting that involves many participants is being quite a challenge. So the situation is rapidly evolving, and with a growing number of COVID cases, there are restrictions that apply to large events to ensure the best sanitary conditions possible. So as I told you in the previous pre-conference, the meeting will be carried out in a hybrid model, with most delegates participating remotely through a virtual platform, and only a very limited number of delegates will attend
Esta reunião está sendo gravada.
At the venue. About 100 delegates will be able to be at the venue, those who already made that choice when they registered for the meeting. We are very sad for not being able to welcome you all in Braga, but this is the only way to ensure that everything goes smoothly in terms of health and safety, which is the most important. In a few days, all delegates will receive the access codes for the virtual platform that will allow a very dynamic experience in the meeting. With regard to poster communications, the poster sessions will be exclusively online, and you must submit your PDF, your poster as a PDF file in your personal area at the registration site. You should have already received an email with instructions, but as I told you before, we will update all the information regarding attendance today at the meeting website. I hope to see you very, very soon, either in person or remotely, and I thank you for your attention.
Okay, Susana, thank you very much for the latest news on the meeting. So for everyone to be clear, the meeting will start on the 14th of July, okay? And you should check your registrations and see if you have everything in order, because some of the sessions will be remotely transmitted, some others will be live, so please make your decisions on time. Okay, I want to remember also that this meeting is the last meeting for the students of the doctoral program in Chemical Engineering and Biology of the Faculty of Engineering of the University of Porto. So for the PDEC-B students, this is the last meeting, so the last conference, the last webinar, and you can then start to upload your recordings after Monday next, okay? For the others, I see already we have a very nice audience, many people from the Department of Chemical Engineering of PhilP. So I welcome all of you and I thank you for being here. And now let me give a brief words about today's talk. The talk will be given by Professor Mara Freire, and the title is Ionic Liquid and Water, the perfect duo to improve the extraction of high-value compounds from biomass. This perfect duo is like, for the ones who like the comics, is like the dynamic duo, actually, which is a very nice reference to the popular culture. Mara Freire graduated in chemistry by the University of Aveiro in 2003, and she got the Best Chemistry Student Award from Dow, Portugal. By the end of 2007, she completed her PhD in chemical engineering by the University of Aveiro. And during this work, she worked at the Federal University of Rio de Janeiro, Brazil, and the Claude Bernard University of Lyon in France. After that, she did several postdoctoral activities at the ETQB2 at the University of Lisbon in Portugal. And then she became assistant researcher at CISECO in Aveiro. CISECO is an Institute of Advanced Materials of the University of Aveiro. Right now, she's the coordinator of the Group 5 of this CISECO, which is the Biomedical and Biomimetic Materials group, and is also the Deputy Chair and Scientific Council of the University. She's also Deputy Chair and belongs to the Scientific Council of the University of Aveiro. She has many recognitions, including several, not only academic works, but also she has filed 7 national and 3 international patents, and is the co-founder of the, I don't know if I'm pronouncing that well, is Hyuptech, which is a spin-off. It was wrong, right? Yeah, okay. How do you call it? Hyuptech. Okay. This is a spin-off. In addition, she has received other awards and recognitions, like she received the Young Scientist Award in 2014. She was among the top 20 women in science in Portugal in 2016. And she was also recognized by the Portuguese Chemical Society in 2018 with the Vicente Seabra Medal. And now she's also recognized as one of the influential researchers by the Journal of Industrial Research and Chemical Engineering. She's one of the most cited researchers in Portugal, and I think up to date, she has already completed the supervision of several postdoctoral researchers, PhD, and master students. In fact, we can only refer to Mara as being a strength of nature, actually. She is a very active, very prolific, and normally she delivers very intense talks. So please be prepared. And Mara, the floor is yours. Thank you very much for coming, and I'm looking forward to enjoy your talk. So please.
Thank you so much. Thank you so much, Professor Joaquim Faria. Thank you so much, Professor Susana Costa. It is a pleasure for me to be here and to have this opportunity to share this talk and to share some of our results and some of our thoughts on this topic. And let me just... good afternoon, everyone. And thank you both again for the invitation to provide this lecture under the topic of ionic liquid and water. Has the perfect tool to improve the extraction of high-value compounds from biomass. So today I will present some of our research lines more connected to green chemistry and on the use of alternative solvents, and they are mixtures of ionic liquids and water. So, and just trying to highlight the work motivation, it is known that in the past few years, and due to their biological properties that range from anti-inflammatory to antioxidant to anti-tumoral features, it has been noted an increase in demand for use of natural compounds over their synthetic counterparts. And this has raised their application in nutraceutical, cosmetic, and pharmaceutical products. So there has been a high interest in natural compounds. However, most of these compounds extracted from biomass and biomass residues have low water solubility, and conventional extraction process for the extraction of these compounds from natural sources, and of course not all, may present several drawbacks. And these include low efficiency, non-selectivity, lengthy procedures, high energetic input, and generally involve the use of volatile and often toxic organic solvents. And this leads to inherent environmental and human concerns. On the other hand, we are all aware that high attention is given today to the separation of integrated and sustainable technologies to produce, extract, and purify a wide range of bioactive compounds and materials. And in this field as well, separation techniques may be complex due to difficulties in isolating the target compound with high yield and with high purity level. And to overcome these drawbacks, and along the years, several techniques have been proposed and used, such as solid phase extraction, liquid extraction, crystallization, precipitation, filtration, and these have been optimized and sometimes integrated to improve the extraction and adsorption efficiencies, as well as to improve selectivity and to decrease the final cost of the target product, and as well as to avoid the use of harsh conditions and volatile organic solvents. And among these efforts, and particularly aiming to reduce the associated negative environmental, health, and economic impacts, researchers have been working on the development of alternative extraction and separation process with greener and more sustainable credentials, and for which the use of ionic liquids has received significant attention. And particularly for those that are not from the field, what are ionic liquids and why have been they used and studied in the field of extraction of high-value compounds from biomass? Well, ionic liquids are organic salts, like shown in this with this chemical structure, and are composed of large and asymmetric cations, and as such do not display an ordered crystalline structures, as it happens with conventional salts such as sodium chloride. And this lack of an organized crystalline structure allows them to be liquid at temperatures close to room temperature. So we can have salts that are liquid at room temperature or other target temperature that can be applied as regular solvents in a wide variety of processes. And due to their ionic nature, ionic liquids display a negligible vapor pressure. So they are non-volatile at atmospheric conditions. And this is the main property that has led to their classification in the past years as green solvents. Finally, ionic liquids display a wide structural diversity. I mean, we can combine a wide variety of cations and anions, chemical structures, and to obtain a wide variety of ionic liquids. We can change the alkyl chain length. We can introduce several functional groups. We can change the family of the cation, of the anion, etc. And in fact, it is estimated that there are 1 million of different cation and ion combinations, or 1 million different ionic liquids. And this number largely overcomes the 600 organic solvents currently used in industry. And indeed, and particularly in this field, this is one of the most relevant properties of ionic liquids. I mean, they can be designed to display high selectivity and high extraction performance to extract target value compounds from biomass. And this figure shows the chemical structures of the compounds extracted and purified from vegetable biomass and resorting to ionic liquid-based strategies, and in which a wide range of terpenoids, phenolic compounds, flavonoids, and alkaloids have been investigated. Ionic liquids and their mixers, both with water or organic solvents, have been directly applied in the solid liquid extraction of added value compounds from biomass, and in which microwave assisted extraction or ultrasonic assisted extractions have been investigated as well to reduce extraction times and improve extraction efficiencies. And of course, these extractions have been followed by separation techniques to purify and enrich the target compound. And these separation techniques, also resorting to ionic liquid-based strategies, mainly include solid phase extraction using materials modified with ionic liquids, and the liquid-liquid extraction using hydrophobic or non-water mixable ionic liquids, or aqueous biphasic systems that are ternary systems majorly composed of water and in which one of the phase-forming components corresponds to ionic liquids. The distribution of the scientific works dealing with each technique for the extraction of natural compounds is also depicted in this figure, together with the families of natural compounds investigated. Overall, and very briefly, the most studied classes of small extractable bioactive compounds extracted and purified resorting to ionic liquid-based strategies correspond to alkaloids, phenolic compounds, and terpenoids. And in these applications, and as shown in this figure, imidazoline-based ionic liquids are by far the most investigated and mainly combined with the tetrafluoroborate, chloride, and bromide anions. And in this field, and particularly given the already large number of publications available and still up to date, the application of more benign and biocompatible options, and this can include ammonium-based cations such as the collinium-based, still lagging behind and highly deserves more attention nowadays. And in the field of extractable bioactive compounds from biomass and using ionic liquid water mixtures, I selected 3 case studies to present today, and they were selected because the recovery of the target compound from the ionic liquid solution was achieved by a different strategy. Well, these examples correspond to the extraction and recovery of caffeine from guarana seeds, the extraction and recovery of syringic acid from pear pills, and the extraction and direct application of an extract enriched in HMR, that is dihydroxymethyl from nuts of Norway's spruce tree. And among the several possibilities of using ionic liquids as solvents, for instance, as pure components, since they may be liquid at room temperature or mixed with organic solvents, why we applied and studied ionic liquid and water mixtures in all these examples? Well, there are 3 main features afforded by the introduction of water. Namely, there is introduction of a more biocompatible and low-cost solvent, that is water. There is a decrease in the solvent viscosity, and which is advantageous to improve mass transfer and extraction efficiency. And there is an increased selectivity and solubility of low molecular weight compounds in ionic liquid water mixtures when compared to pure water or pure ionic liquid. But obviously, in order to be successful in the selection of these solvents, and particularly considering the diversity of ionic liquids that can be used and as chemists, it is necessary to understand first the molecular mechanisms that govern the solubility of the target compounds and their extraction. And in fact, over the years, we have shown that there are 2 main mechanisms responsible for the success of aqueous solutions of ionic liquids in extracting high-value products from biomass, and which in turn depend on the characteristics of ionic liquids themselves. So we have ionic liquids with more hydrophilic characteristics and that tend to act as hydrotropes, and we have ionic liquids with amphiphilic characteristics, I mean containing longer alkyl chains, and that tend to act as surfactants. And when we represent the solubility of a target compound, and in this case we are talking about low molecular weight compounds, has a function of ionic liquid concentration in aqueous solution, this type of solubility profile is obtained. I mean, we have a solubility curve that passes through a maximum, and that occurs at lower concentrations for the case of surfactants. And this behavior indeed allows to increase the solubility by changing the ionic liquid concentration and in turn the extraction performance. So we can develop a process to recover the target compound by simply adding water. That is, we can have an elegant way of maximizing the extraction by changing the ionic liquid concentration, as well as to favor the separation of the target compound from the solvent only by controlling the amount of ionic liquid or water in the mixture, and thus inducing the target compound precipitation. So the first example that I will show comprises the extraction and recovery of caffeine from guarana seeds. And guarana is a climbing plant common in Brazil, and in which its seeds contain about twice the caffeine found in coffee beans. And caffeine is an alkaloid, and particularly if extracted from natural sources, has high interest for application in the nutraceutical, pharmaceutical, and food industries. In this work, we have investigated aqueous solutions of several ionic liquids that allowed us to conclude that at fixed conditions, no major differences in the extraction yield are observed with different ionic liquids. Accordingly, the 1-butyl-3-methyl-imidazole chloride was the ionic liquid selected and used in a second set of assays to improve the caffeine extraction yields, and the reason was that it is a lower cost ionic liquid. And with this ionic liquid, additional conditions, these include ionic liquid concentration in water, the extraction time, and the biomass solvent ratio and temperature were optimized by a response surface methodology. And at optimized conditions, we have obtained extraction yields of caffeine of 9.4 weight percent per Guaraná dry weight. And indeed, this value is significantly higher than the yield obtained by traditional methods, for instance, by salt flat extraction with dichloromethane that leads to a yield of 4.3 weight percent. And with the goal of recovering the target caffeine from the ionic liquid-rich solution, so it was extracted from the Guaraná seeds, and we have now the caffeine in the ionic liquid-rich solution. So here we have used a back extraction procedure to get back the caffeine extracted. And indeed, and as raised in the beginning of this presentation, this could be one of the main disadvantages of using ionic liquids. Well, by being non-volatile compounds, which is good from an environmental perspective, a simple distillation step cannot be applied to recover the target compound, so leading to the need of developing alternative process for the target product recovery. And here, and focus on the back extraction procedure, we studied several solvents to act as the back extraction solvent, and we have identified chloroform, methylene chloride, and butanol as the most appropriate. And even though with a lower extraction capacity, butanol was chosen due to its greener credentials and applied in the back extraction process of caffeine from the ionic liquid water media. And after the caffeine recovery in the butanol phase, we then recovered the ionic liquid water solvent and applied it in new extractions. I mean, we showed that ionic liquid can be recovered and reused as well, and with no losses on the extraction yield of caffeine, and for which the schematic overview of the whole extraction, separation, and recovery process is here shown. Moving now to the second example that is focused on the extraction and recovery of syringic acid from pear pills. Well, in this work, pear pills were used mainly based on data available in Portugal, that is a significant producer of pears. And only in Portugal, about 173,000 tons of pears are produced per year, and with a large fraction being processed by the food industry for the production of jams and juices, and thus generating a high amount of waste. And pear peel that is part of this waste is rich in phenolic compounds, including syringic acid, and whose chemical structure is presented here. And syringic acid has well-reported antioxidant, anti-inflammatory, and antimicrobial properties, and has potential of application in food, cosmetic, and nutraceutical products. However, the main drawback in the extraction of syringic acid is that it is usually carried out with dichloromethane and methanol, and two solvents that should be avoided and replaced by more benign alternatives. And in this work, we performed first some syringic acid solubility tests in aqueous solutions of several ionic liquids to identify the most promising ones, as well as the respective concentrations for the extraction of syringic acid from pear pills. Briefly, these solubility results allowed to conclude that the most promising ionic liquids are those that present characteristics of hydrotropes. I mean, those able to create syringic acid ionic liquids aggregates in aqueous medium. It should be, however, remarked that this type of aggregates are different from those obtained with ionic liquids with surfactant characteristics, and that forms micelles. And among these ionic liquids, the most promising one is again the 1-butyl-3-methyl-imidazole chloride, and agreeing with the previous work, and that the concentration of 3.5 molar allows an 84-fold increase in the solubility of syringic acid when compared to its solubility in water. And another interesting feature of this screening is that most of the ionic liquids investigated lead to a massing in the syringic acid solubility as function of the ionic liquid concentration, and has shown in these figures and being in agreement with have been shown a couple of slides before. So this behavior allows to play with ionic liquid concentration and thus to tailor the syringic acid saturation in the solvent. I mean, by the addition of water, we decrease the ionic liquid concentration and accordingly the syringic acid solubility. And this fact simple results in syringic acid precipitation by the simple addition of water. So a process that will be used in the target compound recovery, as it will be shown in the next slides. And having identified the best ionic liquid and its concentration, we then carry out the factorial planning in order to optimize the extraction of syringic acid from pear pills, and by simultaneously studying the conditions of time, temperature, and biomass solvent ratio. And those results found are here presented. Under the best conditions, the extraction yield of syringic acid found was 1.05 weight percent. And to further increase the extraction yield and sustainability of the process, it was then evaluated the possibility of reusing the biomass with a new solvent, I mean, until the biomass is ocean, and reusing the solvent with fresh biomass, I mean, up to the solvent saturation. And after 5 cycles, yields of syringic acid of 2.22 and 2.04 weight percent were obtained, and these are higher than the values obtained by extraction with dichloromethane and methanol under the same conditions. And 2 of the organic solvents aimed to be avoided, and thus contributing to the development of more sustainable extraction process of high-value compounds from biomass. Taking into account the yield increase achieved with the reuse of the solvent and biomass, it was finally proposed a counter-current process in which both the solvent and the biomass are continuously reused. And also taking advantage of the prior knowledge on the syringic acid solubility, we were finally able to precipitate and recover 77% of syringic acid with high purity by the simple addition of water. And this is an elegant way of recovering the target compound from the ionic liquid-rich solution, which is only achievable by having fundamental knowledge on the syringic acid solubility behavior and molecular level mechanisms involved in the solubility process. And that was here identified as an hydrotrope mediated mechanism. Finally, this recovery step allowed as well the ionic liquid water solvent recovery that was reused in subsequent extraction steps. As shown in the last 2 examples, and particularly because less benign imidazole-based ionic liquids have been used, a recovery process for the target compound was always developed, one resorting to back extraction and the other resorting to induced precipitation. Therefore, why not to explore more biocompatible ionic liquids that could be used in the extraction step and directly applied in the target application, and thus avoiding the need of an extra separation process. And this is indeed the case that I will show as the last example. So in this work, we synthesized, characterized, and used some bio-based ionic liquids derived from glycine betaine for the extraction of HMR, the hydroxymethyl resinol from woods of Norway spruce tree. and while envisaging the direct application of the extract containing both ionic liquid and HMR in cosmetic and nutraceutical products. And the interest in this compound is because it has antioxidant and anti-inflammatory properties, and which have been reported as valuable against breast and prostate cancers. And despite its relevance, the extraction of HMR from biomass is, however, performed with sequential substrate extractions and using volatile organic solvents, and for instance, acetone and water acetone and water ethanol mixtures, and with some of them needing to be replaced by more benign alternatives. HMR was extracted using aqueous solutions of analogs of lysine betaine ionic liquids, and after a first screening on the best ionic liquids to apply, we optimized the process operating conditions by a response surface methodology. And the parameters studied here were the biomass solvent ratio, the concentration of ionic liquid, and the extraction time. And again, under the optimized operated conditions, we got an HMR yield of 9.45%, and which is higher than that achieved with traditional volatile organic solvents. And again, reinforcing the potential of aqueous solutions of ionic liquids to extract small bioactive compounds from biomass, and while overcoming the performance achieved with traditional solvents and traditional processes. And with the goal of applying directly the extract containing HMR and ionic liquid, the cytotoxicity of the ionic liquid aqueous solution and containing HMR extract was assessed in a macrophage cell line, as well as their anti-inflammatory potential via reduction of lipopolysaccharide-induced cellular oxidative stress. And we have found that the antioxidant and anti-inflammatory potential of ionic liquid aqueous solutions enriched in HMR is more promising than the recovered and precipitated HMR, thus opening the door to the use of these solutions directly in nutraceutical and cosmetic applications. So in summary, these results bring new perspectives into the design of new integrated approaches for the extraction and direct application of natural derived high-value compounds using designed and adequate ionic liquids. I mean, if properly designed, ionic liquids do not need to be always removed from the target compound, and an extra step in the process can be avoided, thus decreasing the process time and cost. And after this couple of selected examples and knowing in advance that at the end of 2018 there were more than 80,000 articles and more than 17,000 patents resorting to ionic liquids, I would like to end with a couple of slides to discuss the following question, and that has been largely raised in the past few years in the field of ionic liquids. So, are these examples and other academic ones enough to bring ionic liquids into industry, or are they just an academic curiosity? And to answer this question, I will use some valuable data taken from the book Commercial Applications of Ionic Liquids that was edited by Mark Schifflet and published by Springer last year. And this book comprises several chapters describing applications of ionic liquids, but particularly shows that there are over 50 applications that are either at the pilot scale or have been commercialized. And this number dates from 2020, contrasting with the 13 applications found in 2008, while demonstrating the significant increase in this aspect in the last 2 decades. Therefore, and contrary to some disagreeing comments that ionic liquids are just an academic curiosity, nowadays we have proofs of genuine applications of ionic liquids in the fields of biotechnology, catalysis, pharmaceuticals, renewable fuels, and sustainable energy. And in addition to the companies that were created to explore the development process, and a high number of startups have been created, including the Ria PureTech. Some technologies were licensed as well to relevant companies, and these are the Chevron, the PetroChina, the BASF, Evonik, 3M, and Supelco. And just for curiosity, all these applications are here listed. Of course, I will not enter in details, but what I would like to highlight is the high number of processes involving ionic liquids already at the commercial level. And by the end of 2018, and as raised before, we had a high number of scientific papers and a high number of patent applications in the field of ionic liquids. So the field of ionic liquids indeed experienced a typical hype cycle with increasingly unrealistic expectations, and that were faced until around 2010, and followed by a phase of frustration and corporate withdrawal from strategic investments, and is now on an upward slope of enlightenment. So at present, the field of ionic liquid has just passed the phase of disappointment, and a few percent of applications have indeed reached market adoption, and which will steepen the slope of enlightenment. So it can be anticipated that the first massive applications of ionic liquids will hopefully appear in the next few years. And if we think deeply, this hype cycle happens for any novel and disruptive technology, happening as well in the past with nanoparticles. And this figure compares and very briefly, this figure compares the total annual publications and patents for the terms ionic liquids, molten salts, and nanoparticles, and with search results shown in non-cumulative plots. And the term molten salts resulted in a slow but yet constant growth of publications and patents over the years and up to 2018. And the compound annual growth rate of patent applications for molten salts was around 10% over the past 15 years, and mainly increased over the last 5 years. And this indicates a type of revival of molten salts for modern applications. And here I do believe that molten salts are facing a revival by being tested in some of applications that were developed for ionic liquids. Analyzing, however, the cures for nanoparticles and ionic liquids, a completely different picture emerges. So both technologies show significantly shorter initialization periods and exponential annual growth rates. But the compound annual growth rate over the last 15 years for nanoparticle patents reached 16%, and that of ionic liquid patents reached 21%, so higher than the molten salts field and facing a much faster growth along the years. And the curve shapes for nanoparticles and ionic liquid patents both indicate rapid research or a fast research and development within a variety of application fields and are typical initial growth phase for cross-sectional or disruptive technologies. So summing up, in 2018, there were more than 80,000 published manuscripts and more than 17,000 field patents in the field of ionic liquids. In 2020, 57 applications were found to be at the pilot scale or commercialized. Nowadays, ionic liquids are already produced at the ton scale and precisely to supplement their need in these commercial applications. Furthermore, according to a market study published by the Helmut Kaiser Consultancy, the accessible global annual ionic liquid market raised from $300 million in 2012 to $3.5 billion in 2020. Of course, nowadays, the phase of expectation in the hype cycle was already crossed, and researchers still working in the field are much more devoted to develop process with potential real application. So in summary, all these indicators demonstrate that ionic liquids have passed the stage of just an academic curiosity and will continue to cross the frontier from laboratory experiments to implemented technologies, and certainly will reach a relevant place in the market in the next decade, I do hope. finally, I would like to acknowledge the opportunity to provide this lecture, to acknowledge all researchers involved in the works that I have shown, to acknowledge all financial support from FCT and ERC, and to hope to see you soon all in the 27º Encontro Nacional da Sociedade Portuguesa de Química. Thank you for your attention.
Thank you very much for this nice presentation, Mara. I call this fantastic stuff, very intense, and I think there are a lot of questions. I have several questions on the live chat of the YouTube and several questions also here in the chat. I'm starting with the questions of the YouTube. If you don't mind, I'll read them to you, and I hope you provide an answer to them. And the people who already put the questions on the chat of the Zoom, maybe they can enter the session and put themselves directly. Let's just do it in order. Okay, this was, like I told you, fantastic stuff. And one of the questions that arise here is about the industrial applications of ionic liquids, and this was answered in the last part of your talk. So I'm moving to the next question, which is from Antonio Augusto Riosa Martins. And he's asking, for the environmental performance of the ionic liquids, are the process involving ionic liquids better than other processes in a life cycle perspective, from their production till their final disposal? I think this is a very interesting question and deserves some attention. Yes. Can you comment on that, please?
Yes, that is the other arguing comment related to the ionic liquids field. One is the commercial applications and cost, and the other is the environmental impact, and if they are feasible from that point of view. Well, in most of the development process that most of the development process that we carry out with extraction of value-added compounds from biomass, we also carry out a life cycle assessment. Even though I didn't show any of these results here, what I would like to highlight is that indeed they have a lower environmental performance, but of course, if properly designed, I mean, this is not general. It's not general for ionic liquids. Ionic liquids need to be properly designed. There, you can have an insecticide and you can have an edible ionic liquid. So the chemical structure is quite important, and most of the benefits arise from the recovery and reuse of ionic liquids. So they are non-volatile. We don't have losses to the atmosphere, but we need to guarantee, and at least in fields where it is possible, we need to guarantee that we are able to recover and reuse the ionic liquid to decrease both the economic and the environmental impact.
Yeah, in fact, one of the examples you gave us was the caffeine extraction, which I think is industrial, performed by supercritical extraction. Can you compare the performance of the two methods?
No, I compared with the chloromethane. I was quite bad in that sense.
Because
I didn't find any data with guarana seeds. That was the problem at the time. Maybe there is already. But
yeah, because this was commercially interesting because, you know, Nestle has this patent for doing the extraction of the caffeine, and they filled the patent with the supercritical extraction, which is nowadays is using by the company to do the extraction of caffeine. Okay, I have another question now from Paula Branco, also on YouTube. She said that probably together with caffeine, other compounds are probably extracted, and how is the separation made afterwards? Okay. So she's asking about the post-extraction, how you separate the valuable products.
Yes, that is one of the problems, and particularly with caffeine, is quite difficult to compete with supercritical CO2 in terms of selectivity for caffeine. But not for caffeine. I do remember that the purity of caffeine was around of 80%. So for the separation, and if pure caffeine is aimed, an additional separation step will be needed, and will be mainly resorting to solid phase extraction. But our main idea was to recover an extract rich in phenolic compounds or alkaloids. So trying to avoid the separation of these compounds with high purity or to be used as standards. So at least if you guarantee that the method is reproducible and that it complies with cytotoxicity and environmental aspects, you can employ the extract and not the pure caffeine. So we are not talking about a standard or the real need of a pure compound. But it largely depends on the ionic liquid and on the concentration. For instance, in the work and on the compound being extracted as well. For instance, in the work on the extraction of syringic acid, the purity was quite high. It was around 98%, and this shows a high selectivity to a target compound. Well, with caffeine, we could have go further. It was the oldest work, so it was one of our first works in the field. Nowadays, maybe we have changed the ionic liquid chemical structure and we have paid more attention to improve the selectivity and maybe not so much the extraction yield.
Okay. Yeah, I think in line with that, I have here a question from Pedro Velho. I don't know if he wants to make the question himself. Pedro, you want to enter the discussion? You can unmute yourself and do the question. Okay, if not, I can read the question. So Pedro Velho was together with Dr. Helena Costas, and they were asking, what is the advantage of using mixtures of ionic liquids, water, on the extraction of caffeine, if you use non-biodegradable and toxic ionic liquids, and if you apply alcohol extraction afterwards? Okay, you already answered that partially, but I don't know if you want to comment further on that.
Yes, part of my answer was, in the past, we started with imidazolium ionic liquids. So that work was from 2013, if I'm not mistaken. Nowadays, we almost work no more with imidazolium ionic liquids. We synthesize our bio-based ionic liquids and try to work with this. The need of an extraction, it was carried out with butanol, that even though it is an alcohol, we do not believe that it has so much environmental impact. So
they are even
several
more...
alcohols, you have ethanol and butanol that that comply with some green credentials.
I think they go even more specific on the question, because they ask, how do you precipitate the syringic acid from the mixture? Do you lower the temperature?
No, based on the solubility curves that we have along the ionic liquid concentration, so we can tailor the saturation.
Okay.
And if we move with ionic liquid concentration and add water, what you will have is direct precipitation. So we diluted the mixture by 10 times, of course, knowing in advance the solubility curve, but we didn't change the temperature, we didn't change other conditions. What we did was add water in a known amount, and the syringic acid was completely precipitated, and we recovered it with 77% of syringic acid in the solution, because the solubility behavior has a huge dependence on the ionic liquid concentration.
Okay, fair enough. I have again 2 questions from Augusto Martins. The first one, it comes from distinct from the environmental impacts in the life cycle perspective, which he was asking before. What are the toxicity aspects of ionic liquids in the environment and in humans? Can you comment on that?
Yes, it's like the environmental and ecotoxicity and cytotoxicity. It all depends on the ionic liquid chemical structure.
Okay.
We indeed synthesize ionic liquids to be applied as pharmaceuticals. And of course, we carry out a series of cytotoxicity studies with several human cell lines, and they are non-cytotoxic. But on the other hand, you can have highly toxic ionic liquids. So it depends on the chemical structure. So the chemical diversity is so large that it can be in both extremes.
So basically, it's a matter of choosing the right chemistry for the process that you are looking for. Okay. He has another interesting question, which is about, besides extraction, what are the areas in which ionic liquids can have more impact? And he's asking specifically about carbon capture and utilization. Is that possible?
Carbon capture and
reutilization. So doing the carbon capture and then use that. Okay.
Yes,
so it's one of the big issues of today is carbon capture. Capture and utilization, actually. Yes.
Yes, it is one of the most studied fields in ionic. One of the most studied aspects in the ionic liquids field is for CO2 capture and separation of gases.
Okay. Marius Romano, also from the YouTube, he has another question. Can ionic liquids be used assisting agent in water-soluble compounds for biomass for higher performance extraction?
Can be used as?
Yes. Can ionic liquids be useful assisting? Can they be useful assisting agents in water-soluble compounds for biomass or for higher performance extraction?
Yes, yes, they can.
They
Although we have shown their performance with water mixtures to extract hydrophobic compounds, they are also quite. They also have huge potential to extract water-soluble compounds. And for instance, if we move to ellagic acid or gallic acid that are much more water-soluble, we also have proofs that they perform very well. Even though the solubility dependence with ionic liquid is less pronounced. I mean, that solubility curves is highly pronounced, has more the target compound is hydrophobic. So the more hydrophobic the compound is, the more benefits we take from playing with ionic liquid water mixtures.
Okay, good. So I think we are slowly reaching the end of this session. It's fantastic. We have a very nice and vivid discussion with the people making questions. I think I can end, if there are no more questions, with a comment. Pedro Velho came to the question again. He said that our point about butanol is that if you are going to use it in the end of the process, you could use it from the beginning. There is no need for another solvent. Oops, that's a strong one. Can you?
Yes, we also tried it to use as the extraction solvent, but the performance is not so high. And
Okay.
what we have shown, it did somehow the ionic liquid, and we showed that by SEM electronic microscopy, that the biomass is partially destroyed with ionic liquid aqueous solutions. That should be one of the reasons why this type of solvents has a higher access to extract caffeine than butanol has.
Okay.
Well, we carry out the same conditions, low temperatures. I don't know if we increase temperatures, it will be helpful.
Okay.
But that is a pertinent question, it is.
Okay, good. So let me end in a more positive note. So I have here a comment from Vanessa Vieira, and she said that, thanks, Mara, for the nice presentation. I'm positive that ionic liquids are not only an academic dream. And I think this is the best comment to finish. So Mara, thank you very much for this nice presentation. Thank you all to all attendees for their questions. And thank you all for coming here. So I hope to see you 2 weeks from now in Braga with Susanna. Mara, once again, thank you very much for this nice presentation, and come to the Encontro Nacional of the Portuguese Chemical Society, because we have plenty of reasons and much more interesting chemistry being dealt there. So thank you very much for coming. Thank you all.
Thank you.